We're happy to have with us today Natan Rubin from Ben-Gurion University. Natan is the academic brother of both Boris and myself. He is known for breakthroughs in long-standing problems in combinatorial geometry and computational geometry, such as weak epsilon nets, kinetic Delaunay triangulations. And today he'll tell us about improved bounds for point selections and Halving hyperplanes in higher dimensions.
Thank you, Adam, for introducing me. It's a pleasure to visit you again after 7 years. Today, this talk will deal with the structure of geometric simplicial hypergraphs in D-space. So we have a set of endpoints in which can be assumed in general position. So no hyperplane passes through any D+1 of the points, and we are looking at a hypergraph whose edges are D+1 tuples, which are or vertices, which are basically simplices. Any D+1 vertices describe a simplex this space, and a very fundamental result in combinatorial geometry due to Bárány and Füredi, who were graduate students at Training Institute in 1980, says that if we have, say, endpoints in the plane, then in general position, of course, then one can always fix pierce at least a fixed fraction of the simplices that are determined of the triangle that are determined by these points. So in this case, our simplices are triangles, and in fact, this fraction tends to 2/9, which is known to be tied with constant. And it's known as it became known as the first selection theorem, and it was generalized by Bárány in 1982 to simplices in arbitrary d-dimensional space. So we again pierce a very large fraction, a considerable fraction of the simplices that are determined by all sorts of D+1 tuples of points from the given ground set of n points. And the problem has been studied extensively, and one has to mention, for example, and unlike the planar case, the bounds are not so tight in higher dimension, so this constant remains somewhat of a mystery. We got to mention.
So CD is this piercing?
Yes,
right. Okay.
it's what is called what the space covering number, or there are all sorts of names to it. It's yes, how many simplices? If you are looking at all the possible n choose D+1 simplices, how many of them you can pierce by a point?
Okay, thank you.
It has been studied a lot. It's a mystery to determine this constant. A major breakthrough of Gromov shows this lower bound on this constant, how much you would pierce. And on the other hand, you have this upper bound that you cannot for some point sets, for some collection families of points that you cannot pierce more than this fraction. So this is the state of the art, and this is the so-called first selection theorem. So even this constant is not well understood, and it bears relation to wonderful studies in overlap properties of geometric hypergraphs, etc., etc. But today we are going to discuss an even harder version of the same problem, where we in fact have only we have a hypergraph which contains only some epsilon fraction from among the d-dimensional simplices. Again, we have d+1 uniform hypergraph of simplices, and it has density epsilon. You have this fraction of edges of the possible d+1 tuples, and the second selection theorem states that there is always a constant exponent, so that you are in such circumstances you are always going to pierce at least epsilon to this exponent beta b fraction of the simplices. So you begin with some dense epsilon dense hypergraph, and and then you have how much you are going to pierce with a single point is going to be epsilon to some constant exponent. In what follows, we are going to call it the selection exponent. And in this case, it's not quite the constant, which depends on the dimension. It's the exponent in the dependence on the value of epsilon on the density. And the first result showing that such an exponent does exist at all was due to Alon, Bárány, Füredi and Kleitman. And they showed this pretty nasty exponent, which is 4d+1 to the power of d+1, and we'll shortly explain where this comes from. And later on, it was improved by Blagojevich, Mačke, and Ziegler, 20 years later, who showed in 2010, who achieved a slight improvement, or not so slight, in the exponent, in the sense that you have, instead of 4D, you have 2D here. But what they did, they proved a better colored Turberg result, which lies at the root of Alon, Bárány, Füredi and Kleitman bound. So in fact, they did not change the paradigm, and of course, in the plane, you always have something way better, which is obtained in ad hoc manner. So we have arbitrary close to 3. Oh. Yes, it's all right. So several questions are in order. Does this selection exponent matter? The answer is sounding yes, because The best known estimates for the notorious K-set halving hyperplanes K-level problems in computational geometry, they currently in all dimensions 5 and higher, they rest on this selection exponent. So if you remove the selection exponent, you improve bound on a very fundamental quantity which underlies the bulk of computation geometry. And okay, so it matters. And another question that one may ask, does this exponent has to be exponential on its own? Does it have to be this huge some constant times d to the power of some constant multiple of d? Why it's not something nice like d or d square or something why do we have to suffer? And in fact, in this paper, we are showing that it's enough to take the selection exponent. One can show that it's no more than d to the 5 plus pocket change. So all these horrors of something d some say 2d 4d something to the power of d plus 1, it's unnecessary. And let us say a few words about the important relation to the Halving hyperplanes problem. Erdős asked one of the famous Erdős problems asks, suppose you have two points in the Euclidean plane in general position, and how many ways you can split them evenly by a line. And it comes down to counting so-called halving edges, where you are looking at all the possible edges so that the line, at all the possible pairs of points so that the line through them would split the remaining two n minus 2 points into 2 even parts, each of size n minus 1. And the same of course, holds in higher dimensions. So we are dealing with the so-called halving simplices, so that the supported hyperplanes are splitting the remaining point set evenly, or almost evenly. And in fact, Lova showed that the number of halving edges was smaller than order of n to the power of 3/2, and there was a massive body of work, and then they improved the planar bound for to n to the power of 4/3, and in free space there is this compound of order of n to the 5/2, and there is more tedious ad hoc estimate in 4 dimensions, but all of them using some variants of or higher dimensional extensions of the crossing lemma, but
Can you put the back to just one?
yes.
Okay, thank you.
But when we deal with general dimensions, dimension 5 and up, there is one known way that is used to obtain an upper bound for Halving simplices, which is based on the observation of Lovash that a generic line in this space crosses only order of n to the power of d minus 1 halving simplices. And if we project this hypergraph of halving simplices one dimension down, it follows that it does not contain a too deep point. So there is no line crossing more than this amount of simplices in dimension b minus 1. So if we prove some, if you use a second selection lemma theorem, it eventually implies this upper bound on the number of halving simplices. In other words, if this hypergraph of halving simplices cannot be too dense, if it were dense, then by projecting it, we would obtain a dense hypergraph, we would obtain a dense point, we will obtain a point piercing many of these simplices, which would lead back into a vertical line piercing many of the halving simplices in this space, which is of course impossible according to Lovash. So let's say a few words about the roots of the exponentiality of the selection exponent. It stems from the Kolot-Verberg result originally from Zivadjevich and Brechica, which was further improved by Blagojevich, Machke, and Sigler. It says that if you have d plus 1 point sets, and, each of size whose size is bounded from below by a second constant, which is Kolot-Verberg constant, then one can always find d plus 1 disjoint set of representatives, one from each set. So basically, d plus 1 simplices involving one vertex from each of these sets, with the property they will all have an on-empty intersection. And another ingredient behind the previous bound was the so-called Erdős-Simonovich theorem, which was a completely combinatorial non-geometric result, which said that if you have a dense hypergraph, say d plus 1 uniform hypergraph, but it works for any uniformity parameter, then you have many copies of completed bipartite hypergraph with size of size t, where t is convenient. We can take t to be the Kolot-Verberg constant. So you find many Kolot constant. We find many copies of the Kolot-Verberg configuration with many, and we find many d plus 1 tuples of intersecting simplices. In this way, we use a we can use, for example, fractional Helly result to conclude that one must be able to pierce many of the simplices by a single point. But the root of the exponentiality of the selection exponent lie in this reliance on Erdős-Simonovich, which is a completely non-geometric result. It does not use the underlying geometry of the hypergraph, and it leads to a really bad exponent. So in this paper, we establish this sort of selection exponent, which is e to the power of 5 plus pocket change. This delta is arbitrarily small constant. So basically, when we are speaking of the selection exponent, there is also the constant fraction when we look at so when we are speaking of this omega, there is also the hidden constant factor. So the the smaller is delta, then the worse is this constant factor hidden in the lower bound, in the asymptotic lower bound. But this is the order of magnitude. And so it says that if we have n points in general position in this space and an epsilon fraction of all the possible d-dimensional simplices spanned by these points, then there is always a point piercing this amount of simplices in our hypergraph. And as a corollary, it instantly yields an improved bound for the Halving hyperplane problem. And here are some ingredients of our improved estimate. So, quite surprisingly, the first ingredient is Matuszek's simplicial partition theorem, which is very well known to combinatorial geometrists among us, but much less so to the combinatorists. And we also use the structure of hyperplanes crossing a family of up to d+1 simplices in this phase. And we also, a very interesting ingredient of its own interest, it's a new and efficient Turán-type result for semi-algebraic hypergraphs. And it's quite remarkable that when we deal with the selection exponent, we don't assume that our hypergraph is semi-algebraic, but one can still benefit from such results for semi-algebraic hypergraphs by looking at that and by going into dimension d square, or which is because you need d times d+1 parameters to represent a simplex. So we are going to use semi-algebraic results in a certain parametric space used to represent simplices, and uses polynomial partitions, and it's inspired by the machinery of MNETs, so Mustafa and Bray, to improve the so-called polynomial regularity of Fox-Bach. So this is used eventually to obtain a much better selection exponent.
So you're using two completely different partitions.
Yeah. There are several partitions, yes. And there is also color selection result of Roman Karasov, which is kind of colored. It can be considered a colored variant of the first selection theorem of Bárány and Borovshev already. So we also use this. We have to use something. So if you let us say a few words about Turán-type lemma for semi-algebraic hypergraphs. So if you have what is a semi-algebraic hypergraph? Say let's say it's k partite. So you have k parts, k families of vertices, which are points in this space, each of them, and you have we assume that we have an epsilon fraction of all the possible edges. We assume the density is at least epsilon, and we also assume that its edge set is cut out by a certain semi-algebraic set of bounded description complexity. In this place, we go dimension d times k, which is used to represent all the possible k tuples of points. This is the assumption, and such hypergraphs have proven to be tremendously useful. And in fact, this is the main class of hypergraph that arise in computational geometry. And under such circumstances, whenever this is the case, we can find a complete, a very large, complete k-partite hypergraph within such a k-partite epsilon dense hypergraph. So you have, say, all these combinations. So you have k parcel that parcel that all the combinations of one versus from each part is inside our edge set, and also there is a very large number of such combinations, and it's a vast improvement upon a similar lemma of Fox, Bach, and Suk, because unlike the result, our result does not depend on the degree of the polynomial equalities and inequalities which are used to determine the semi-algebraic hypergraph. And of course, there is further work in progress in wake of this result, which I may present now a bit.
Can I ask a question? Do you have any idea about whether the exponent in E2 is anywhere near the right value?
I have no idea. Here, right?
Yes.
So basically, most parts are of size epsilon to the p times the appropriate size. So we gain an epsilon to the b fraction of the appropriate size. And yeah, it's a good question whether this exponent has to be really b or something else. There is lots of work around so the so-called Zernkiewicz problem for semi-algebraic hypergraphs. But all these results live in a somewhat different setting and seek to optimize different things. So let's mention, let's say a few words. What is Matuszyk's simplicial partition, which is not so well known for most combinatorialists, those who did not study with Michał Szalik. So we have, say we have endpoints in this space, and the point is that one can obtain an almost even partition of these points into parts of size between n over r and 2n over r. And so that each part is enclosed by a simplex. And so there is an order of R parts enclosed by simplices, and there's such a partition so that any hyperplane would cross only a small amount of these enclosing simplices. And the rest of the parts would be somehow separated from this hyperplane. So the enclosing simplices will be totally missed. This is a very useful result for in computational geometry, say for geometric range searching. And here we will see some of its applications in combinatorial geometry. So the question is, what's going on? Yes. So the question is, how come this partition comes useful for piercing many simplices? Yes. So we are looking at all the possible d+1 tuples. Rather than looking at d+1 tuples of points, we are going to look at d+1 tuples of the simplices in Matuszek's partition. So we are basically, we will look at them as super edges. And we say that such a d+1 tuple of simplices is tight if whenever we choose some representatives, one point from each simplex. And so we are going to look at all such simplices. Then they all have a common non-empty intersection. Then it is tight. So basically, they must be sufficiently apart so that if we look at all the convex hulls of subsets of size d of them, then and we look at the union of these convex hulls. Say here we're looking at the convex hulls of pairs. There is always, then there must be a hole that is not covered by any of these partial convex hulls. And this is exactly what guarantees that there is a non-empty common intersection to such simplices involving one representative, one vertex, having one vertex in each of the simplices. So this is so if you are lucky enough, then the vast majority of such a d+1 size families, so the simplices in Matuszek's partition are going to be tight. And therefore, whenever we have not just simplices of our hypergraph, but simplices that whose vertices come from given such tight d+1 tuple, they are all taken care. All of them can be pierced at once by a single point. So let's make it specific. Let's give a kind of rough draft of how a proof might look like. We are going to show that only this small number of small fraction of the d plus 1 tuples of opposing simplices in Matuszyk's partition, they are not tied. Which will so any d plus 1 points forming a simplex in our epsilon dense hypergraph, it falls in one of these d plus 1 tuples, hopefully, except for a small number that when two vertices fall into one partition simplex. But mostly they fall into different d plus 1 tuples. And if you show use a sufficiently large partition parameter, that would guarantee that the vast majority of at least half of our edges in our hypergraph are going to fall into tight d plus 1 size subcollections of simplices, and therefore using the pigeonhole principle, one of these collections of simplices of d plus 1 partition simplices is going to contain many many edges, many d plus 1 tuples of points, which are actual edges in our hypergraph, and all of them are going to be pierced at once, and that's the end of the story. So our task comes down to bounding the number of the families of d plus 1 simplices in Matuszyk's partition, which are not tight. Let's call them loose. So what does it mean for simplex to be loose? So that if you look here, if you consider all the partial convex halves of d plus of d simplices out of the d plus 1 simplices in question, there is going to be some common intersection, so there is not going to be any hole in the middle. So we say that such a family is pinned by a point if this point just lies somewhere in this convex hull. And our strategy for bounding the number of loose families of d plus 1 simplices boils down to these two basic steps. For one can show that using the basic properties of Matuszyk's simplicial partition, that no point is going to pierce more than this number of to pin more than this number of loose families of d plus 1 simplices. This is the first step. So this is basically what we gain from Matuszyk's simplicial partition. So this is the upper bound on how many loose families can be pinned by a single point. There is also a lower bound on the same quantity, which will be stated in the terms of the supposed density, which we don't know, of the hypergraph of loose families of d plus 1 simplices in Matuszyk's partition. So for this, we will use semi-algebraic Turán-type results, and surprisingly, the color selection result of Karasov. So if we combine them, it will obviously follow that this density is bounded by this power of R. So it will mean that this hypergraph of loose families cannot be large. So we actually not be the exponent must be small. So let's see in a few words where comes the upper bound on the pinning number of the hypergraph of the loose families. It boils down to the fact that whenever we have a family of, say, D+1 simplices spin, there is a hyperplane through the spinning point that crosses at least D members of the family out of D+1. And if you repeat it for all the families and use some elementary geometry, it can we will show that if the pin collection is too large, then we will end up crossing too many of the simplices in Matuszek partitions, which we assume to not to be the case. As for the lower bound, suppose that we have many hyperedges in the so we want to suppose we have large amount of hyperedges in the hypergraph of the loose families. So we are going to pierce many large fraction of the loose families by combining the following properties. We will use our Turán-type result for semi-algebraic hypergraphs, and as we said, we are going also using the color selection theorem of Karasov. Basically, we are going. So we already seen this result. We are going to so our simplices are going to become vertices in a certain representation space of dimension d times d+1. How many coordinates we need to represent d+1 vertices, but this can be reduced to d square. And if the hypergraph of the loose families is, I have 2 minutes, right?
Yeah.
If our hypergraph is epsilon dense, then we are going it's going to, because it's actually semi-algebraic, because the looseness is semi-algebraic property. Then we are going to find a pretty large complete d+1 partite hypergraph within it. And by choosing, and we are going to combine it with the result of Karasov, which says that if you have D+1 families of points, which are considered as D+1 colors, and we are looking at all the colorful simplices involving 1 point of each color, then we are always going to pierce a fixed fraction of these colorful simplices. So if you pick, if you are looking at the complete D+1 partite hypergraph of loose families, so that any edge represents a loose family. And if we are going to choose one representative from every simplex, then we can we are going to obtain such a D+1 colorful configuration of Karasov, and eventually find a point piercing many of the simplices connecting D+1 representatives, each time piercing some pinning some loose family. So this is the general idea. So we did not, though the original hypergraph is not semi-algebraic, but the property of being tight or loose is semi-algebraic. It's determined by the position of the vertices of the simplices. And here we can combine the semi-algebraic Turán-type lemma with the result of Karasov. So to conclude, we obtained a far more efficient proof of the second selection theorem using polynomial regularity instead of the wasteful Erdős-Simonovic theorem. We no longer depend on the colored Tverberg constant, whatever it is. And we also made the first progress in 30+ years on the case at Halving Hyperplanes in the general dimension D. And more semi-algebraic regularity results are on the way, probably. And we have a convergence of ideas and tools from several areas of computational discrete geometry, like color selection lemma, Matushik simplicial partitions, extremal results for semi-algebraic hypergraphs, the polynomial partition of Boot and Kass, which can be used to obtain such results. And so the inevitable conclusion, so the conclusion is that future is bright and success is inevitable. You know where it comes from.
Nowhere.
The movie Paris When It Sizzles.
Which movie?
Paris When It Sizzles.
Paris.
When it sizzles.
Oh.
So future is bright, success is inevitable. So, thank you.